Hey guys, welcome back to Genius Learning. In this video, I want to show how to get the Lagrangian of the system and how to find the generalized coordinates. All right, so we have this plane in green that slides to the right as this little box here slides down. Okay, so we have this slide moving to the right as this slides down. And we want to figure out the position, velocity, kinetic energy, and potential energy of the system. All right, so let's figure out the generalized coordinates. All right, this here is an angle of alpha. Okay, and this picture here is the exact same thing as this one. It's just a little bigger, so that way we can draw some stuff in here and be very clear about what we label. Okay, so let's label a couple things in here also. So the distance from the top of the plane to the small box, we're gonna label as B. Okay, and the distance that the plane, the bottom of the plane, is to the origin, I'm gonna label as A. Okay, and that's so that way we can make one generalized coordinate for the whole system. And I'll show you what I mean by that in a second. Okay, so this space in here, we're gonna say that it's the entire length of L minus B. Okay, so this is gonna be L minus B in here. Okay, so let's see. The entire length minus this will give us this length in here. Okay, now let's look over here for a second and figure out what our x and y coordinates should be. So if we draw a line down here from the center of the mass, right? So we can estimate that this box is really small, and so that the center of the mass is right around there. And this is going to be a right triangle. Okay, so if this in here, this length is going to be L minus B, then opposite over hypotenuse is going to be L minus B sine alpha. And that's this entire side right here. Okay, and then similarly, this side down here is going to be cosine. So it's going to be adjacent over hypotenuse. And we're going to have L minus B cosine of alpha. Okay, and that's for this side down here. Okay, so that's how we're gonna see the position of the small box in relation to the position of the plane. Okay, so now let's begin and let's label our position or our coordinates. Okay, so the position of the box, we'll go first. Okay, so the position of the box, we found over here, X and Y, right? So let's look down here. We are a distance away, an A, away from the plane. And we have this distance here away until we get to the box, okay? This distance right here is this. So we are a distance A away from the plane, and L minus B cosine is this length right here, which is lined up with the box. So our X position is going to be A plus L minus B cosine of alpha. All right, so it's just this plus this. That's how we're going to get to the X position of this box. All right, now the Y is just going to be this height. From 0 all the way to here is this side right here. Okay, so L minus B sine alpha. Okay, so this is the position of the box, and now we need the position of the plane. Okay, because we have two things in our system that's moving, right? The box is moving down while the plane is moving to the right. And we're gonna label the plane as X capital M, so we don't confuse the two X's. Okay, so in the X position, the distance away from the center of the plane, the front of the plane, is gonna be A. Okay, so the distance away of this plane here from the origin is A. And in the Y, 0, because here at the bottom is where we're measuring. It's not moving up and down, so we're just gonna keep it at 0. Okay, now that we have the position, let's look at our velocities. So the velocity is taking the derivative of the position. And before we take the derivative, let's identify what's moving in our system. Okay, A, this distance right here, is gonna get bigger as the plane moves towards the right. So this distance is changing. Okay, so we can take the derivative of that. And this distance B is getting bigger as the box moves downward. So we can also take the derivative of that. Okay, so we're gonna say X dot is equal to A dot and negative B dot cosine alpha. Okay, let me show what I did there. So if I take this and FOIL it out, right, I'm gonna have X is equal to A plus L times cosine, so L cosine alpha, minus B cosine alpha. Okay, so this right here is this whole thing on top. It's just FOILed out. And so L, the length of the plane does not change. This is constant. And the alpha is also constant because the angle of the plane is not changing. And so this term right here, when you take the derivative of a constant, is just 0. And so when we take the derivative of this side, okay, we could take the derivative of B, which we did, B dot, and then we leave cosine alpha alone because alpha is not changing. All right, so we're left with this and this down here, okay? And now let's look at the Y. So Y dot, we're gonna do the same. Okay, so here we're left with L sine alpha minus B sine alpha. And again, L, the length here is not changing and alpha is not changing. So this term here we don't need. So it turns into 0 once we take the derivative. The only thing we keep is this term, alpha is not changing, and we take the derivative of B, and so we're left with B dot, the negative that came with it, and sine alpha we keep the same. All right, so that's the derivative for the box, right? So this is for the box. And now for the plane, we got X dot of M, right? A is changing, so we can say A dot, and we're not moving up and down in the Y, so the derivative obviously is going to be 0 as well. Okay, and so this is for the plane. All right, so now let's put those two things together in our kinetic energy term. Okay, so our kinetic energy we can write as T is equal to 1/2 mv squared, or we can write T is equal to 1/2 m x dot squared plus y dot squared. Okay, so we're gonna use this right here. But our total kinetic energy has to represent both of these objects in our system. And so we're gonna write T is equal to the kinetic energy of the box plus the kinetic energy of the plane. Okay, so lowercase m is for the little box, capital M is for the plane. All right, so let's write our total kinetic energy. So T of little m, right? And so T for both of these values looks like this, but we'll be replacing x dot and y dot differently. So let's see. T of little m, right? We're gonna have 1/2 m and x dot squared plus y dot squared. We come over here where we have our x dot and y dot, and we're gonna write the x dot first. So we're gonna have a dot minus b dot cosine alpha squared. That's our x. Plus, now we're gonna plug in here the y dot. So it's negative b dot sine alpha squared. Okay, that's the kinetic energy term for the box. So that's this one right here. Now, plus, let's do the kinetic energy term of the plane. So looking at our kinetic energy term again, our x dot is gonna equal a dot right here. So we're gonna have 1/2 m a dot squared plus our y dot is 0. So 0 squared. Even though we don't have to write that, I'm just gonna write it so we can see that both kinetic energy terms are filled in how we derived here our x dot and y dot. So let's put all this together. Okay, so here we're gonna have to FOIL this out, and let's see what we get. So we're gonna have 1/2 little m. Okay, so little m. We got a dot squared minus 2 a dot b dot cosine alpha. Okay, that's putting those two together, and then the last term here is going to be plus b dot squared cosine squared alpha. Okay, so that was just for this, and now this term here is going to be positive b dot squared sine squared alpha. Okay, close parentheses, and then our last term here is plus 1/2 big M a dot squared. Okay, sorry, this should be big M. All right, so the difference is that this is little m and this is big M. And to try to avoid confusion, I like to write this little line right here with the little m, and the big M I don't. So that'll be the difference. Okay, so now we have things that we can combine. All right, so we got cosine squared, sine squared. Okay, and then we have this a dot squared and an a dot squared over here. Okay, so let's do this in a couple parts. So t is gonna equal 1/2 little m. I'm gonna distribute it in, so little m a dot squared minus 1/2 little m, and this term here, which is 2 a dot b dot cosine alpha, and we see that the 2's cancel. And then before I distribute this into these two terms here combine to be just b dot squared, because we have a cosine squared and a sine squared, which turn into 1. So we're gonna have plus 1/2 little m b dot squared for the last two terms, and then plus this over here, we have 1/2 big M a dot squared. All right, so now it's clear to see that we can combine a dot and a dot to have a cleaner, simplified kinetic energy. So the 1/2 and the a dot squared of both of these terms will be pulled out. Okay, so we'll have 1/2, we'll have a little m plus big M, and then a dot squared. So this term here came from this first term and the last term. Okay, we have this middle term still, which is minus little m A dot B dot cosine alpha plus 1/2 little m B dot squared. Okay, so this is our kinetic energy term. All right, so now let's find our potential energy term. Okay, so let's see, potential energy, right, is U is equal to mgh. And so we can also write that as U is equal to mgy, because our height is represented by the y-axis. So we need the same system as this here, okay? We need to follow that. We need the height for the small box and we need the height for the plane, okay? So U is gonna be made up of U, or the potential energy of the little box, plus the potential energy of the plane. But for the plane, there's no height, okay? So the plane sits on the 0, right? Y equals 0. And so we don't need to worry about it, but we would need to worry about it if it was at a height. Okay, so now we're just gonna focus on little m, and we know the y for little m, which is the box, which is right here. Okay, so let's put that together. We're gonna have U is equal to mg L minus B sine alpha, okay? And depending on where we put our potential energy term, so let's say we made U equals 0 down here at the 0, we would put a negative here on our potential, or if we made our potential equals 0 up here, then this would be a negative term because we would be below the U. Okay, so wherever we choose to make our potential energy 0 is the reason why this would be a negative or a positive. Okay, so it's a negative if our potential energy is 0 all the way at the top of the plane. If it's at the bottom, it would be different. Okay, so just keep your eye out on that. And now that we have the potential energy and the kinetic energy, the Lagrangian is just going to be a combination of both. Okay, so I'm not going to write it out, but all you have to do is write this for your kinetic energy minus this for your potential energy. Okay, there you go.